To answer the question in the video title, we first have to understand what do we mean by the word dimension. Easy, right? The minimum number of coordinates which you need to describe the exact position of a point in a particular shape is its dimension. For example, to describe any point on the line, we need only one number, the distance from either end. So a line is one-dimensional. In case of a 2D shape such as a square, we need two numbers, the distances from two adjacent sides. But the purpose of this video is to give a new meaning to the word dimension. Let us first take a line of fixed length, say 4 cm. Now if we zoom in on the line by a factor of 2, the length of the line becomes 8 cm, so it has doubled as expected. Now take a square with length of each side being 4 cm, its area is 16 cm square. Now zoom in by a factor of 2. The length of each side becomes 8 cm and its area becomes 64 cm squared. Now here comes the interesting part. In case of the line, the length increased by a factor of 2, which is the zooming factor raised to the power of 1. In case of the square, the area increased by a factor of 4, that is the zooming factor raised to the power of 2. We can define this power to be the dimension of these shapes, and this really works. For any basic shape, it's quite easy to prove that this method really gives the correct value of the dimension we are all familiar with. However, using this method we can get some intriguing results. But first, let us come up with a more generalized term, like measure, which is nothing but a placeholder that is length for a line, area for a 2D shape, volume for a 3D shape and so on, so that we do not get confused while going into uncharted territories. Now let's begin with the triangle. Divide it into 4 regions like this, cut out the middle portion, repeat the same thing with the remaining triangular regions and so on till infinity. This is the Sierpinski triangle. Now you know the drill, zoom in by a factor of 2, but consider this, the original shape was made of 3 such new shapes, so the measure has to have increased by a factor of 3. So the dimension d, as we saw earlier, has to be such that 2 to the power d is equal to 3. Rearrange some terms and voila, we get the dimension to be around 1.585. This type of dimension, called the Hausdorff dimension, is not only useful in cases of abstract mathematical shapes, but is extremely important as a measure of roughness of coastlines, which are themselves real-world fractals. By the way, fractals are nothing but shapes in which more details appear as you zoom in. So the answer to the original question we asked is yes.